everyone. Welcome back to Grade 12 University Physics with Mr. Stone. So we're finishing up here looking at relativity. So this is the last sort of lesson we're going to talk about the whole idea of special relativity. We're not going to be able to get into general relativity, a little bit too much for this course, but hopefully this has sort of cleared up some of the questions you may have about things like time dilation and E equals mc squared. That's what we're going to look at today. Okay, so what we've talked about so far is how time and length are relative things. It depends on the speed at which a frame of reference is traveling. Okay, and not just inside the frame of reference, but outside the frame of reference as well. How you're looking at a moving frame of reference. And things get a bit strange because space and time become interwoven into this new idea of space-time. Now, what this leads to, a little bit beyond this course, but what this also leads to is something very strange. The idea that speed has an effect on mass. In the exact same way as time gets longer, masses also increase. As we increase speeds, the mass as we view them from the outside, not from the inside. If you're inside the spaceship, your mass isn't changing. But if you're looking at a spaceship going by you near the speed of light, the mass of that spaceship has increased dramatically. And it has to do again with that gamma coefficient, right? This gamma here. And we're multiplying the rest mass multiplied by this gamma term to give us what we call a relativistic mass, the mass in which we view it from that moving frame of reference. So as an object's speeds increase, its mass, when viewed from a moving frame of reference, increases by the factor of gamma. Now what this means, this is why there's a speed limit in the universe. It's for this reason it's impossible to accelerate an object to the speed of light. Once we try to make it go faster and faster, it's getting heavier. And we know that F equals ma, the heavier something is, the more you have to push it. And that mass, as it approaches, as it gets closer and closer to the speed of light, it gets much, much larger. And once we get, fractionally close to the speed of light, its mass is, a million times heavier, billion times heavier. So we have to eventually, to accelerate it up to the speed of light, if you want to take something that has mass, anything that has mass, for it to travel at the speed of light, you have to use all of the energy in the entire universe to do that. You have to use an infinite amount of energy to get it that last decimal place. Okay? This is a very strange idea. And it leads us to an interesting question. We're creating mass, aren't we? When we're doing this, we're speeding something up. We have an object and we accelerate it closer and closer to the speed of light. It's going very, very fast. It's getting very, very heavy. But we can't create mass. Right? Law of conservation of mass states that matter can't be created or destroyed. Where is this matter coming from? Where are we just magically coming up with mass? Sorry, and the answer is energy. We are converting energy into mass, or more generally, mass and energy, relativistically, are indistinguishable. We have to change our law of conservation of mass and our law of conservation of energy. We have to combine them now into a new modern physics law, which is the law of conservation of mass energy, because energy and mass are indistinguishable. Or, in another way of saying it, E equals mc squared. This is the famous equation that you've probably seen all over the place. That it says that the energy of something is equal to its mass times the speed of light squared. That's a huge number, right? That's 9 times 10 to the 16. So something that might be very, very small, like 1 kilogram, has 9 times 10 to the 16 joules of energy. It's a ridiculous amount of energy. It's not really saying that. It's saying that that all energy has a mass equivalence, and mass has an energy equivalent. Okay, and notice that when we write this equation out, we're talking about the relativistic mass. So as we increase the speed of an object, we're going to give it extra kinetic energy. And eventually that kinetic energy is no longer distinguishable from its mass. The mass that we have, that we're giving it, the mass has some equivalence. And that mass, right, has some energy equivalence in the order of 10 to the 16 joules. So once we start increasing its kinetic energy up to the point of 10 to the 16 joules, we're just gonna have to add it to it. It's no longer, we can't talk about where is the energy coming from, the mass or coming from the object itself. So very, very fast things. When we start talking about very, very fast objects, things that have very, very large, amounts of kinetic energy, we have to no longer talk about energy or mass. We have to talk about them as meaning the same thing. Energy and mass have an equivalency at these high energies or high speeds, and is defined by E equals mc squared. For example, if an electron and a positron, those are antiparticles of each other in the standard model. Every particle that exists has a antimatter version, and an electron has a antimatter version called the positron. If those two combine, if they hit each other, they're going to cancel each other out. They're going to destroy all their mass and convert it entirely into energy. And we're going to actually have a release of 2 photons of 511 mega electron volts. Every time we have a positron electron annihilation like that, it'll always give off 2 photons at that energy, because that energy is equal to the mass of that electron. The reason there's 2 and not just 1 is that we still have to conserve momentum, but we'll get to that in a little bit. So there has to be 2, one going one way and one going the other way. But in that case, we have mass. We have something that has mass, an electron, 9 times 10 to the negative 31 kilograms. A positron, 9 times 10 to the negative 31 kilograms. They're going to annihilate each other. And when they do that, they're going to release the energy that mass is equivalent to by E equals mc squared. Okay? Now, if those 2 electrons or that electron and positron are traveling very, very fast, then we're actually going to release more energy, because we're going to have to also combine the relativistic mass of those electrons and positrons. Right, we're going to have to also add the kinetic energy. The kinetic energy that those things have also has to be released in the photons. But if they're just traveling at regular speeds, a positron and an electron will cancel each other out and release the energy that their mass is equivalent to. Okay? And this leads to all kinds of things like nuclear power, nuclear bombs, the sun. The sun works in this manner. When a hydrogen and a hydrogen nucleus and another hydrogen nucleus combine. So these 2 protons, hydrogen nucleus is just a proton. 2 protons combine in a certain way. There's a bunch of steps involved, but they make a helium. And that helium, the binding energy that holds the helium together, is a little bit less than the initial hydrogens. It actually takes 4 hydrogens. 4 hydrogens combined to make 1 helium. But the binding energy that holds it together is a little bit less than the mass equivalence of the initial protons. And that difference in mass is released as energy. And that energy eventually reaches us as solar energy and provides all the life on Earth, all the energy that provides all the life on Earth. Okay? We'll talk about this in lesson 9. So in Einstein's original work, the way he wrote it was that kinetic energy is the mass difference, or mass defect, some people call it, the difference in the masses between the relativistic mass and the rest mass, and its energy equivalence. So we multiply by c squared. Anytime you want to talk about an energy equivalence of mass, just multiply by c squared. Or if you want to talk about a mass equivalence of energy, we divide by c squared. But if you see here, the kinetic energy is just the difference in masses times c squared. So the kinetic energy of an object is just the difference between the relativistic energy and the rest energy. Okay, it's all different ways of saying the same stuff, but that's how Einstein wrote it in his paper in 1911. This is general relativity paper, not his special relativity. That was 1906. We've gone a little bit farther, and the math the math that developed in those 5 years to get this theory completely correct is way beyond this course. So let's not worry about it. Okay. Now you may ask yourself, okay, so kinetic energy is this? This is the expression for kinetic energy, right? This thing here, that's not half mv squared, right? Half mv squared is what we know of kinetic energy from unit 3, 2, 3, I forget. Where's this coming from? Are they the same thing possibly? Well, let's see. So kinetic energy is the difference between the relativistic energy and the rest energy, or mc squared minus m naught c squared. And then we can just factor out c squared, and we know that m, the relativistic mass, is the rest mass divided by the square root of 1 minus v squared over c squared, that gamma term. Okay? Now, I can factor out m naught. So I have m naught c squared here multiplied by this scary looking bracket here. Now I'm going to do a little math trick that involves some calculus that is what you'll learn in possibly first year. Something called a Taylor series. I can approximate this thing here by a series, an infinite series. That means an infinite sum of derivatives using calculus terms here. Okay, and if I just take the first, since v is much smaller than c in the classical case, right? That's what we're talking about. The classical case, we're talking about things much slower than the speed of light, many orders smaller than the speed of light. Things we talk about here, like 100 meters per second, 1,000 meters per second, even things like that, non-relativistic. That's a lot smaller. That's many orders of magnitude slower than the speed of light. So this term is very small, this v squared over c squared. We squared it, so it even gets smaller, right? So it's a very small term. So we only take the first two terms in the infinite series. And it looks like this. Don't worry about where that's using something called the Taylor series, and we're just taking the first two. The ones cancel, and that's where the half shows up. Then the c's cancel, and we're left with half m naught, the rest mass, or just half mv squared, just like we know in typical dynamics. Okay, so in the case where v is much smaller than c, this still works. This is what we call a classical correspondence. This is a very important thing that had to be proven with all of this new ideas of relativity. We're coming up with all of these new things, and we have to show that everything that was correct before in typical Newtonian physics is still correct. There still has to be a classical correspondence, a classical equivalency. When I talk about velocities much smaller than c, this theory has to distill itself into the typical Newtonian physics. Newtonian physics, everything that we've done, is not wrong. Okay? This is very important. We're not proving anything that we've done prior to this wrong. We are merely proving that it's a special case. We have to come up now with a more general theory of how the universe works. And in that general theory, there has to be a special case. In this, now we're talking for velocities much smaller than c, that is Newtonian physics. So Newtonian physics lives inside our Einsteinian relativistic physics in the case where velocities are slower than the speed of light. We haven't proved anybody wrong. Okay, everything is now within it. It's a special case. As when we talk about things being special, like Einstein's special theory of relativity, it is a special case for inertial frames of reference. Once you want to talk about non-inertial frames of reference, things accelerating frames of reference, we have to then jump into general relativity, which is a more general view of the universe. And there's that involves all non-inertial and inertial frames of reference. And then there's a subclass of that where we're talking about inertial frames of reference. And then there's a subclass of that where we're talking about slow speeds, which is our Newtonian physics. Okay? All right. Sorry for the digression there. So let's do a quick example. We're going to measure mass of a neutron in some particle accelerator. The mass of the neutron is 1.71, not 1.68, which is the typical mass of a neutron. So how fast is it traveling? So we can take our relativistic mass equation here. We can divide both sides by m naught and then square everything. And then flip everything. We just flipped the fraction here. And then I multiplied both sides by c squared, just because I didn't like the v squared over c squared fraction. So I multiplied everything by c squared. Then I brought I isolated for v squared, factored out the c squared, and then take the square root of both sides. Okay, so this is just doing a little bit of algebra to get v by itself. And then I'm going to plug in 1.68, that's the rest mass, divided by 1.72. The 10 to the negative 27s cancel. I didn't write them down. A lot of writing there that we could save. And then that works out to 0.19 c. So really, when you travel, if you have an neutron traveling at 20% of the speed of light, its mass is changed. Its mass is increased by this tiny little bit. This 0.03 times 10 to the negative 27 kilograms. Okay, so mass is no longer an absolute thing as well. Mass depends on how we look at it. If I'm looking at that neutron, the exact same neutron in the rest frame, if I'm traveling with it, if I'm somehow traveling in a rocket ship at 20% of the speed of light directly next to that neutron, I would measure its mass to be 1.68. But outside of it, in my rest frame, in that lab frame of watching it go by at 20% of the speed of light, its new mass is 1.71 times 10 to the negative 27 kilograms. Okay? All right, so let's try another one here. Now, one of the important things that we have to talk about, an important thing we have to talk about here is the use of electron volts as a energy. Okay, so because everything is going to be small, because everything is going to be in the order of 10 to the negative, like 13 joules, things like that, we're going to now use a new unit, which we're going to call an electron volt. And that electron volt is 1.602 times 10 to the negative 19 joules. Okay, so let's say we have an electron. It's traveling at 86% of the speed of light. What's its rest energy, total energy, kinetic energy in the lab frame in electron volts? So how do we do this? So rest energy, pretty straightforward. Rest energy is the rest mass times c squared. And that comes out to 8.19 times 10 to the negative 14 joules, or 0.511 mega electron volts. That's that number I told you before. 0.511 mega electron volts is the, I think I said 511 mega electron. I should have said kilo electron volts before. Sorry about that. So 0.511 mega electron volts is the energy equivalence of the mass of one electron. Then to get the total energy, we know that the rest mass is going to be gamma multiplied by the relativistic mass is going to be gamma times the rest mass. And we can plug in for the 0.8c. Now 0.8c squared divided by c squared, that's going to cancel the c's, so it's just 0.86 squared. And that works out to 1 mega electron volt. And then the kinetic energy is just going to be the difference. All right. And you see, this is why we're using this mega electron volt unit. Now, this is where things get a bit funny, because when we talk about, let's say that Large Hadron Collider, when we talk about its beam strength, what is the energy in the protons that are whizzing around in that synchrotron? we're not talking about when we say it's, what is it, 13 tera electron volts. We're not talking about the energy. We're talking about the total energy. We're talking about sorry, whoa, went too far. The total energy. So this term. So that includes the rest mass and its kinetic energy. Because the kinetic energy now actually has an energy equivalence, and the mass has an energy equivalent. Right? So when we talk about something, we could say that this electron, when an electron is traveling 86% of the speed of light, we can call that a 1 mega electron volt electron. Okay, just this is what we're going to use these terms for. Okay, when I talk about a 1 mega electron volt electron, let's talk about its total energy, and mega electron volts is just using this here. Okay, all right. So big ideas here. Mass is not absolute. Energy is mass. Mass is energy. These are some big, awesome, frightening ideas. But for now on, I just want you to work on these problems. It's just 1 to 6, pretty straightforward, using these formulas. And the answers are all on the website. And best of luck. All right, I'll be talking to you later.